Okay, so let's start today's talk. So today I'll talk about some of the group theoretic aspects of physics. So perhaps I mean, maybe you already know some of it, but some of the things maybe new to you. So in any case, you will learn something new here. Okay. So today I'll talk about uh, why at all we bother group theory, at least in the context of physics. First thing is that, and I'll give ample examples so to motivate you that why should you pursue the study of group theory if you want to pursue physics. Okay, so I mean, for that, let me first give you the classic example as we always give. So let's say you have so we start with the symmetries of a triangle like this. So let's say I mean I was not able to draw it properly, but okay, let me draw it again.
Sir, if you will draw and hold, it will become triangle, na? Yes.
It has. So let's say this is what it is, and so let's say I do some operations on this triangle. So there are multiple operations. So let's say I denote these vertices as ABC, and if I make a rotation about this axis that passes through the center of the triangle by 120-degree anti-clockwise or clockwise, either it won't matter. Then if I rotate it, the triangle will still remain the same. And if I again do so let's say rotation by 120 degrees, rotation by 240 degrees, rotation by 360, which is again the same as doing nothing, rotating not at all. So these are three operations which will leave the triangle as it is. But is that all? No, actually there are three more. So one is this. If you take a reflection about uh, median that passes through the vertex A, so that's one case. So let's say I'll call it as reflection about A. I mean, reflection about a line or median that passes through A, and similarly this, and similarly this. So if you think about it, then let me also write them as RB or RC. So let's say this is the triangle on which you operate R120. It will still be the triangle. But now what happens when you do that? Let's say you apply rotation and then reflection and then rotation, then reflection, let's say this. So it turns out that it will again be sum of so this operation will equal to be either of these six. So in that way, the symmetry operation on the triangle is closed. So you can do any number of operations, but then you will find that operation equal to an element of the set itself. So mathematically, this is known as the closure property. So if you have a set, you define some sort of binary operation between elements, and if you do the binary operation, and if you again get the same or element of the same set, then it is called closure. Okay. So okay, perhaps one very good motivation to study group theory. So this is the case of discrete group, as we call discrete group, because you have some elements that you can count 1, 2, 3, 4, and so on. But it is also possible that the group may have infinite number of elements that you may not count, that you may not be able to count. But then that is also discrete group, although that's not finite group, that's infinite group. But then you also can think of uh, groups that have some in a way some sort of continuity. So let me give an example. So let's say if you consider this two-dimensional coordinate system, this is x comma y, and you fix a point that is, let's say, x comma y, and you imagine some other coordinate system, let's say this one, x prime, y prime, and this you rotate it keeping the origin same by an angle theta. So then now you can see that you can vary this angle continuously. You can vary theta angle continuously. And so what is that? That remains the same. So if you think of that, let's say the length, let's say this length. So if this length is x square plus y square is square root. So this length will not change upon the rotation of the coordinate system. So it will be the same whether you rotate the system or you don't rotate the system. So in that way, this operation that when you rotate the coordinate system, the length does not change. So in that way, it's a symmetry. So in this case, the elements are changing continuously. Okay. So as we will see that this is also a group and we call it as SO2. So what is the meaning of S and O2? We will see soon. There are some more examples. So perhaps a very strong motivation to study group theory is in the context of particle physics. So if you think of various sort of interactions, so we have various sort of interactions like let's say weak interactions, strong interactions, electromagnetic interactions, and gravity. So gravity, as we know, has not yet been quantized and it is not the part of the standard model of particle physics. But then if you talk of, let's say, the strong interactions. So it is known that strong interactions is mediated by something called as gluons, which are bosons, which are again bosons. And there are 8 types of gluons. So one observation is this. Now let me talk about the weak interactions. So weak interactions are mediated by 3 bosons, W and Z plus minus. So you have 3 such type of mediators that will mediate the weak interaction. And lastly, the electromagnetic interaction. So electromagnetic interaction, as you know, that you have just 1 photon. So that's fine, okay? But we study these interactions based on some sort of symmetry operation, or that something does not change under when you make some changes in the system Lagrangian, for example. So it turns out that the symmetry group for or that we use to study strong interaction is SU3. For this is SU2. For this is U1. So for SU3, you have 8 generators. For SU2, you have 3 generators. And U1 is generated continuously by only 1 parameter. So can you see the link? You have 8 types of gluons, you have 8 generators. You have 3 mediators for weak interaction, you have 3 generators. You have only 1 photon for electromagnetic interaction, you have 1 continuous parameter. So in that way, it's a very deep link between these two. So the number of generators for a group is equal to the number of the mediators corresponding to the interaction for which you are using that symmetry group. So in that way, it's very useful. So there are some more contexts. So if you take the context of quantum mechanics, so it turns out that, so for example, if you take the hydrogen atom, so hydrogen atom, as we know that it has n square fold degeneracy if you remove the spin degree of freedom. And if you consider some more exotic example, for example, the case of infinite 3D potential well. So in that case, it's 2L plus 1 fold degenerate. Okay. And also in the 3D harmonic oscillator, it's again 2L plus 1 fold degenerate. So it turns out that, so although in the hydrogen atom case, you have spherical symmetry in this case also, in this case also, but why is there difference between the level of degeneracy? Why it is n square and why it is 12 plus 1 and 12 plus 1? So the reason can again be explained using group theory. So it turns out that, so first thing is that the larger the symmetry group or the more the symmetry of the system, the more will be the degeneracy that you will find in the system. Okay. Is my voice audible? Because no one is saying anything.
Yes, it is audible.
Okay. Nikhil, for you too?
I think Nikhil is lost.
Okay, Nikhil is not there. Anyway, we will continue. So for the other cases in which you have like 3D infinite potential well, and also if you take the 3D harmonic oscillator. So you have this level of degeneracy. So degeneracy means that you have so many states, but all of them have the same energy. So this can be this can be understood on the basis of group theory. So a general principle is the more the symmetry, the more the symmetric the system is, more the level of degeneracy it will have. And it's sort of very intuitive, because if it's possible that that you can get to some other state by some sort of rotation, only just by some sort of rotation, then it will have the same energy, because intuitively you can think that the energy should not depend upon the orientation. So in that way, intuitively you can think of this, that more the number of symmetries, more the number of degeneracies. Okay, so I think it has given you enough motivation. And there's one more example I wish to give. So that's related to my own research in general relativity. So which is in the Poincare-Gauge theory of gravity. So as I said that although in the standard model we have the quantum field theories for strong, weak, and electromagnetic forces, we don't have yet a theory for the gravitational interaction. But and one thing is that these three interactions are based on gauge groups. So is it possible to understand gravity as well in that way? So Poincare-Gauge theory presents such an example. Okay. So okay. Okay. So it has been done for gravity also, but it is yet to be quantized, or at least now the whether it's quantizable or not has not yet been studied as of my knowledge. Okay, so first, in order to understand what group theory is, we will start with very simple examples of discrete groups, and then we can go to more complicated examples related to Lie groups, which are, as I said before, these are continuous groups, as you can see here. So this was the example of a continuous group, SO2. Okay, and I will describe the meaning of what is the meaning of SO2. Okay, so perhaps it's now the good time to talk formally about what a group is. So you consider G some set which has some element, let's say A, B, C, D, and so on. So I call G, and let's say I also have a binary operation, let's say cross. So what does cross do? Cross will do something like this. Cross will take two elements of G and will map them again to the same set G. So for example, if you take A and B, multiply them together, you will get some element, let's say F prime, which is again in G. So this is the meaning of closure. And then you also have associativity, which means that you do this or you do this, they are both the same. And there must be the existence of an identity element, which means that identity is an element which corresponds to doing nothing to or no operation at all. So that's the identity, and also the inverse operation. So let's say so in the previous example, so inverse rotation would mean that if I have rotated this system, this dotted system, by an angle theta in the anti-clockwise direction. So the inverse operation means, or the existence of inverse operation would mean that there is something that you can do to the system so that it becomes it can rotate clockwise in the clockwise direction. Okay, so this is so if a set has all these properties, we call that set as a group. Okay, so let me perhaps I'll give you now let me say a few more words about that. This one, the rotation group. So let's say you want to, so let's say this is the XY plane, the usual Cartesian plane, on which you have X comma Y as a point. So, and I'm denoting it by this vector. So now I want to see what happens when you rotate it by some angle theta. Let's say this is the new coordinate system. Okay. So this is your coordinate system, so that it becomes X prime and Y prime. So now you can write the coordinates, the coordinate of this point in both coordinate systems. So let's say in other coordinate system, it becomes x prime, y prime. Okay. But now you see that the distance or the length of this vector will not depend upon the coordinate system you are using. Okay. So it should be x square plus y square square root x prime square plus y prime square. Okay. So what it means that, so let's say I'm performing a rotation. So in the new coordinate system, you can, if the new coordinates are x prime, y prime, then you can get them by operating by some matrix on the column vector xy. So in the present case, if this angle is theta, then you can show that this is equal to this. So this is a rotation matrix. Okay. So what it does. So if I were to write it in a short way, I would write r prime equals r times r. And so if r is this, r prime is this, so therefore r transpose is would be a row vector like this. So then the length of the vector or the square of the length of the vector will be r transpose r dot is equal to, or yeah, fine, this one, and or so this should be equal to this quantity. Okay, because the length of the vector will not change. So this means, so this gives us the condition that r transpose r is equal to identity. Okay, so this is the condition for orthogonal matrices. So if a matrix R satisfies this condition, then I call R as the orthogonal matrix. Okay, now so orthogonal matrix are all such matrices which preserve the length of the vector. Okay, so because there can be many matrices, but they have to preserve the length of the vector. Now if I take the determinant on both sides, then it gives determinant R transpose determinant R equals determinant of identity matrix. But this is 1 because the determinant of identity matrix is 1, and we also know that the determinant of matrix and its transpose are the same. So this means the determinant of R is equal to plus or minus 1. So if we take determinant R is equal to plus 1, then these are the special orthogonal matrices. So that's why I write SO2. So whatever I wrote here, so this is an example of the special orthogonal matrix. There is one more possibility when determinant R is equal to minus 1. So, okay. So for one example for this would be, let's say this one, 1, 0, 0, minus 1. So what it does, it's sort of, so if you apply it on x comma y, so this will give you x comma minus y. So it has inverted the y coordinate. So what it has done, so let's say if this was here, so after you make this, after you apply this matrix on this vector x, y, it became x comma minus y. So then this is this x comma minus y. But still the length of the vector, as you can see, has not changed. So this has to be, so this must always be the case. Okay. So this was the case of 2D rotation, but then now you can also rotate in a vector in 3D. So in that case, you get the orthogonal group 3 for the 3 rotations. And if again the determinant is equal to 1, you would say that you are talking about SO3. Okay. Okay. So and one more example of a group would be, let's say now I take the example of a discrete group by just simple multiplication, 1 minus 1 I minus I. Let's say I take these 4 elements or rather this Z4 set, and to check whether this is a group or not. So you can, and the multiplication or the composition is just a simple multiplication. Okay. So now you can check that it satisfies all the 4 properties that I listed before. So let us check them. 1 minus 1 I minus I, 1 minus 1 I minus I. So when I multiply them, I'll get 1 minus 1 I minus I. So I'm just doing a simple multiplication, okay? So now minus 1 times minus 1 is plus 1, minus 1 times I is minus I, minus 1 times minus 1 is 1, and this is minus I minus 1, and oh, this is plus I. Oh, sorry. This is minus I.
On the top, you have written -1 at the last. It is minus I.
Oh, sorry. Okay, thank you. Okay. So then it is minus I and I. So then this is minus I, this is minus 1, and this is 1. Fine. And so on. So as you can see that if you multiply two elements of this set, you will again get something in the set again. So what so I can also give a physical meaning to this. So if you think about it, it's just equal to this. I n times pi by 2, where n is equal to 0, 1, 2, and 3. Okay. So this is equal to this. And what is physically means? It is the rotation of a square. Okay. So let's say if you take this square. So then if you rotate it by, so first operation is you don't do any rotation at all. It remains the same. And then you make a rotation by exponential minus I pi over 2. So that's minus I, or yeah, exactly minus I. So if you do the okay, I'm sorry. Yeah, this one. So then this is I only. So it means that you are rotating it by 90 degrees. So it will still remain the same. And minus 1 corresponds to the rotation by 180 degrees. And minus I corresponds to a rotation by 270 degrees. So the square will still be the same. So maybe it's possible to do that. Oh no, you cannot rotate it. Yeah, like this. So let's say this is this, and if you rotate it by 90 degrees, you will get this. Oh, sorry. And if you rotate it by one more 90 degrees, then you will get this. So the square has not changed, although I'm not able to do it very perfectly because I'm changing the size of the square, but you can see the point. And then if you rotate it by one more, so now I have already rotated by 180 degrees. Now I will do a further rotation by 90 degrees. So this is what you get. Yeah, this is what you get. So the square has not changed. So this Z4 is now the same as just the rotation part. Okay. Because as I have talked about before, the symmetric group of triangle is known as D3. And the symmetric group of a square is known as D4. So it has rotations, 4 rotations, but it also has reflections. So these are the 4 reflections. So if you take reflections about all these 4 axes, you will still get the same square. Okay. Okay. Fine. Okay. So in the discussion that goes further, I'll primarily talk about the continuous groups. So let me start with okay. So I'll primarily talk about. Okay, so for that, let me take the example of just the rotation, because rotation is very easy to understand. Okay, so let's study rotation once more. So what we have been doing, let me also use that other frame. Okay, so then, so this is x comma y, this is x prime comma y prime. And what we are trying to do here, we are trying to study. So let's say you have this point x comma y. So you can write this the same coordinate in the x, this let's say O frame or O prime frame. Although the coordinates will change, but the length of the vector will still be the same. Okay. But then, so initially you perform the rotation by some angle theta. Okay. But then you can also say that I will not do it in just one go. I'll do it in a large number of times. For example, if you want to rotate by, let's say 15 or let's say 30 degrees. So you can make just one rotation by 30 degrees, or you can say that you will do it in 10,000 times by rotating by this much degree. So if you rotate by 30 over 10,000 times, you will still get 30 degrees. So is this point clear? Because this is very important to understand, because this will give a sort of foundation for the Lie groups. So is this idea clear?
Yes, sir.
Okay, fine then. So let's say I want to rotate it by theta degrees. So I will not do it in just one go. I will rotate by theta over n, and I'll do it n number of times. So if I let's say, so I can also take this limit. That if I take this limit, I still get theta, because n and n will cancel out. Okay. So this is the operation I have in my mind. Okay. So we saw before that if the rotation that you do the rotation on this O system so that it becomes O prime, then in order to preserve the length of the vector, it has to satisfy some property. So for example, this R transpose R equal to identity element. So it has to satisfy this. Okay. So now let me write. RS. So since I'm doing very small rotation, so I'll write this as this. Let's say, so one is no rotation at all. So you can think of it in a continuous manner. Let's say, so this was your XY frame, and or rather the O frame, and you make a very small change. So since it was nothing before, then if you make a small change, then it will be off. Then it will be the same as you're making some small change in the identity element. Okay, so the diagram would be to see this, it would be good. Maybe this. That you made a very small change. So this rotation, that you're doing this change to the system, is represented by A. Okay, because now I'm trying to rotate by very small angle. So if this is this, then if I plug it in back in this equation, I'll get I plus A transpose, because you see A is very small. So A square, A cube, and other higher order terms in A can be neglected. So this is R transpose R, I plus A. So this I can take as I plus A transpose plus A, and I've neglected higher order terms. But then this is again the same as I, because whatever matrix you will get, that has to satisfy this property, because these are all orthogonal matrices. So they have to satisfy this property. So that gives A transpose plus A equals 0. So this means that A transpose equals minus A. So what is this condition? Can anyone tell? A is antisymmetric. Hello?
Sorry,
Are
I
you
was
lost?
muted. I was reacting on a muted condition.
अच्छा हाँ ठीक है. So is this clear?
Yes, sir.
Okay, fine then. So so now since we are considering only 2 cross 2 matrices, how many such matrices are there? So let's do that. So let's say if I take A as this, A, B, C, D, then A transpose is equal to A, C, B, D. But this has to be equal to minus of A. So A, B, C, D. So what it gives? A equal to 0, D equal to 0, C equals minus B. Okay. So then I can write A as 0, B minus B 0. Do you agree?
Yes, sir.
So there is only one possibility of doing that. Okay. There is only one possibility. So, or maybe I can use some other, because B is any general variable. So B can be anything. So, but just for the sake of it, I'll write B as theta. Just let me write it as theta. The small parameter theta. Now theta can be anything. So I'm just renaming the variables. I'm not doing anything else. So this is, I'll take theta outside, 0, 1, -1, 0. Okay. So now what happens? So this is called the generator. Okay. So now I've written A is equal to theta times, let's say this is J. Okay. So this is a generator of rotation. So you do it many number of times. I mean this thing. Because I've written R equal to I plus A, you do it many number of times, then you can generate a finite rotation. Now I'm only talking about infinitesimal rotation. That's very small. Let's say if you want to rotate by 30 degrees, you are doing 30 over 10,000 degree rotation. And you will do it 10,000 times in order to get to your final rotation. Okay. ठीक है, idea तो ये है, ठीक है. So then R is equal to I plus theta J. ठीक है. So now if I want to rotate by a very small angle, let's say okay, sorry, by theta over n, where n is a very large number, then this is I plus theta over n times j. So now I will do this rotation n number of times. So what I will do, I'll do theta over n rotation n number of times. And I'll take also this limit, because if any n is, so I'm doing it, I'm doing very small rotation a large number of times in order to get a finite rotation. But do you identify what is this? Perhaps you have seen this already. Can you identify this? Anyone? Richa, Nikhil?
No, sir. In first hand, I can't. Maybe I have seen, but I'm not speaking.
Yeah, you have seen this already, but maybe now now you are not able to recall this. So you remember this? N goes to infinity. 1 plus x over n power n equals e power x. And that you can check very easily. You see, and this is also the definition of E, the Euler number. So if you put x equal to 1, so then this is this.
1 by n.
Yeah, so you can very easily see, because n goes to infinity, this is a very small number. So then you can use the binomial expansion. So then you will write it as 1 plus n into 1 over n plus n into n minus 1 over n square over 2 factorial plus n into n minus 1 n minus 2 1 over n cube over 3 factorial and so on. So then if you take limit n goes to infinity, so then this cancels out. So this is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. But what is this? This is just e.
This is e to the power. Sorry.
E to the power 1 or just
1. Yes.
So this also holds for matrices, because you remember this is I is not just a number, it's a matrix, but you can still write it as theta j. So what it means, and we'll also check this. We'll also check this, that what it means, that you can either do a rotation, let's say 30 degrees in just one go, or maybe you can do that rotation in 10,000 steps by doing 30 over 10,000 amount of degree of rotation. But then it should also be equal to, but we already know what that rotation is. This is cos theta, sin theta minus sin theta and cos theta. So that should be equal to this thing that we have to check. So if it is not equal to that, then our whole formalism is not of any use at all. Okay. So then it can be checked very easily because we know that let's say e power m is defined to be 1 plus m square over 2 factorial and so on. So if you do this, because you know the form of j, so what is j? 0, 1 minus 1, 0. So then e power j theta is equal to 1 plus 0, 1 minus 1, 0 times theta plus theta square 0, 1 minus 1, 0 whole square and so on. So if you add up this series, you will get what? I mean, it's very easy to see, but still, let's do it. So what is this equal to? 0, 1 minus 1, 0, 0, 1 minus 1, 0. So this is then minus 1, 0, and 0 minus 1. ठीक है? ऐसा करके आएगा. And so on. So then eventually you will be able to show कि ऐसा आ जाएगा. यहाँ पे cos theta आ जाएगा, sin theta minus sin theta cos theta. ठीक है, ऐसा करके आ जाएगा. If you sum this series, you will get the same result back as you should. But then, so what's the point of doing all this? As we already know that the result is going to be that. ठीक है. Maybe for 2 dimensions, it's very easy, but not in general true for 3 dimensions. 3 dimensions, where the analysis become a bit complicated, but then if you want to generalize it to any number of dimensions, then it will be really very hard to do it this way. So that's why we rely on this thing, that in what way the group is generated by generators. So let's say, and that's the final thing that we will do today. So let me just discuss the SO3 case. So SO3, so here S means that it is special. So what does this mean? That I'm looking for matrices, 3 cross 3 matrices, because 3 here represents 3 cross 3, and O means orthogonal. So orthogonal means that R transpose R equals I, and special means that determinant of R is equal to 1. So these are the 3 conditions that are there in this SO3 thing. Okay. So I'll again use the same thing, that I'll say that I'll do whatever rotation I want to do with the help of very small change. So I'll write it as I plus A, and then I'll again use those conditions, because R transpose R equals I will lead me to R transpose, A transpose A transpose equals minus I. But now, since these are 3 cross 3 matrices, there are 3 such generators. So let me again do that. A, B, C, D, E, F, G, H, I. So this is A, and if you take a transpose of this, you will get A, D, G, B, E, H, C, F, I. So this means all the diagonal elements are 0. A equals E equals I equals 0. Okay. And then B equals minus D, H equals minus F, and what? C equals minus G. So now there are 3 such possibilities. So there are 3 such generators. So then you will write JX as, let's say this one, 0, 1, minus 1, 0, 0, 0, 0, 0, 0. This is one. JY 0, 0, 1, 0, minus 1, 0, 0, 0, 0. And JZ as 0, 0, 0, 1, minus 1, 0, 0, 0, 0. I may have switched the order, but yes, this is what you get. Okay. So now, as we did before, for any general rotation in 3 dimensions can be written as exponential. Let's say theta jx plus phi jy plus psi jz. If you know, how can you reach that angle? By rotating about various axes by theta, phi, and psi. So that's one part. So, I mean, in a way, we are studying the whole group in terms of not the basic or not the rotation matrices, but how these matrices are generated by generators, these 3 generators, Jx, Jy, Jz. Okay. And they also have certain properties. So these properties are given in terms of how do they, because these won't commute with each other. Jx, Jy, Jz will not commute with each other. So all the properties that you want to know about these generators is given by the Lie algebra. So this is how we define the Lie algebra. I mean, so Lie algebra has some more details in it, but the commutator is also a part of it. So let's say it is equal to some constant times Jy. Okay. So after you know the Lie algebra of a group, of the Lie group, then you know, because any matrix. So let's say this is A, which no, not A, sorry. So let's say this is rotation R1, which is equal to this, and rotation R2 can be e power theta prime Jx, phi prime Jy, psi prime Jz. And you want to know what is R1, R2 equal to. Then if you know these commutators between Jx, Jy, Jz, then you can easily do this computation. So in that way, if you know how the commutators behave, you sort of can combine any two elements of that group. So it can be generalized to any number of dimensions, for 3, 4, 5, any number of dimensions. So in general, if you go to the next dimension, that is n equal to 4, you will have 6 generators. And in general, you will have n into n minus 1 over 2 generators. So if you are in dimension n, so accordingly, you can construct the Lie algebra and study the rotation in any arbitrary dimension. So that would give, so of course we, if I talk of, let's say, its application in particle physics, so I would be more concerned with SU2, which we have not discussed today, or SU3, or let's say U1, but we have not done the discuss today. But then SO3 is very, very, very useful when you study problems in quantum mechanics having rotational symmetry in them. So as I talked about before, if a system has rotational symmetry, then, or some sort of symmetry, then it will also exhibit degeneracy. So now let me go back to the observation that I talked about before, that, yeah, this one. So hydrogen atom has n square fold degeneracy. Of course, if you go to the spherical polar coordinate system, and 3D, it's infinite potential value has 2L plus 1, and 3D harmonic value has 2L plus 1. So it is because that it has, these systems have SO3 symmetry, but hydrogen atom has SO4 symmetry as well. Although it has SO3, but it has SO4 symmetry as well. That's why it is more degenerate as compared to these two cases. Okay, so so this is what I had to discuss today. So maybe I'll stop here.